I've opened up a trace file called DNS-OK so that I can examine the structure of DNS queries and DNS response packets. In this trace file, we have a user who is attempting to connect to iana.org, and because they don't have the name and IP address relationship information inside of their cache or in a local host file, they go out on the network through the resolver process and they do a DNS query. In this middle window, we can see the standard structure of a DNS packet on an Ethernet network. We have our Ethernet header, and in there it will say that IP is coming up next. In our IP header, we have a field that tells us that UDP is coming up next. In the UDP header, we're going towards port number 53, which is defined as the DNS port. And here's the DNS data in the packet. We can see on this line that it's a query. I'm going to right mouse click and expand the subtree so we can see all the different parts inside the DNS query. The first thing we have is a transaction ID. This 2-byte field is used to associate DNS queries with DNS responses. In the flags area, which is 2 bytes long, we can see that we have individual bits that have meanings and groups of bits that have meanings. The very first bit in there indicates that this is a query packet. The next 4 bits together indicates the opcode. An opcode of all 0 indicates that this is a standard DNS query. If we see an opcode of 2, it means it's a server status request. If it's an opcode 5, it means that it's an update packet. We see indication that this packet has not been truncated or shortened, and that recursion is desired. Now, recursion is the process of making a query for information of a DNS server, and if that DNS server doesn't have the information, they will go on your behalf and ask another DNS server. You don't have to go and start asking multiple DNS servers. You ask one DNS server and it will ask other servers on your behalf. We have reserved bits as well, and then we have the bit that indicates that we will accept non-authenticated data, which is the default for DNS communications. Now here are the 4 sections I mentioned before: questions, answer resource records, authority resource records, and additional resource records. You can think of resource records as just the database records that you get back when you make a DNS query. Let's look a little further in this packet at the query that was made by this client. We can see on this line, here's the summary of the query. The query was for www.iana.org, and the user was asking for a type A, which is a host record. And the class type is IN, which stands for Internet. Let me take you out to the IANA page where they list these different type numbers. I'm out at www.iana.org/assignments, looking at the DNS parameters page. When you go through this page, you'll see that all the types are listed there, and there's type A, which is a host address. We possibly can set up a system to do a DNS query looking for an authoritative name server. Or maybe we're looking for an MX record. That's the mail exchange. We want to find the mail server for a specific company, perhaps. This is where you'll get the master list, and you'll see the reference there is RFC 1035 that you can get online at www.ietf.org. So you can see it's a very simple structure for standard DNS communications. Now I'll look at the reply packet. Now, because I've expanded that subtree in the previous packet, it is expanded in this packet, and you can see that we have a relationship set up for us already in Wireshark. The very first packet said that the reply was in packet number 2, and in this packet it says the request was in packet number 1. If we're on a network that's just heavily loaded with data and there are all these packets in between the DNS queries and responses, we can use that information to tie the two together. The time field there tells us the time between the DNS query and the response. And that is a field that we can build a filter on. We can right mouse click and say we want to prepare a filter based on the selected value, and you can see that there is a filter syntax for DNS.time. You probably wouldn't do it as equal signs, you probably do it as greater than and look for a time value. Something like that. Here we can see the transaction ID, and we'll go to the packet before it and see if it matches the transaction ID, D48A, and the second one is D48A. So yes, they do match, so we know that this response goes with the previous query. Now we go to the flags field. We can see that the first bit is set to a 1, which means that this is a response. In addition, we can see recursion was desired and recursion is available, saying that the server can do recursive queries. This bit indicates that the answer, or the authority portion, was not authenticated by the server. If this bit is set to on, it simply means that the DNS server that responded has authenticated this information according to its own policies. We'll scroll down. Now the interesting thing with DNS communications is that the question is always restated. So we can see now in this sort of summary area of what's contained in here, what's inside of each of the 4 parts. We have one question, we have one answer with a resource record, we have no authoritative resource record answers and nothing additional in there. Here's the query that our client originally made, and here's the answer. We have to expand that one because it wasn't one of the subtrees in the previous packet. So we can right mouse click and expand the subtrees all in one shot there. There's the answer that our client got back. There's a summary line saying this is a type A, a host address, the class is internet, and the address that they've been given is 192.0.34.162. There's the name, restatement of the question all the time. And this is the time to live value. This time to live value tells the client how long they're allowed to cache this information. If the time to live value is set at 0, it means that the client can use this information once, and that's it. It's not allowed to cache this information, and if it wants to get back to this web page again, it's going to have to do another DNS query. Then we've got the data length field that tells us we have 4 bytes of data following, and there's the address. So, pretty simple structure for DNS communications. In this section, I want to show you how we can create a standard DNS capture filter, and that will be one where we'll look for all DNS traffic, whether it's a user that's going out and making a DNS query or it's a DNS zone transfer. And the difference between those two is that a normal query goes out over UDP, whereas a zone transfer uses TCP. After that, we'll build a DNS display filter, a very simple one, and then we'll go through building advanced DNS display filters, where we look for a specific value in a specific field, or we look at the amount of time between DNS queries and DNS responses. So first, let's start by building our capture filter. I'll select to show the capture options window, and then I'll click the capture filter button. To build a new capture filter, I'll click the new button, scroll down. There's my new filter. I'll give it the name of DNS. And the filter string will be based on the port number used for DNS traffic, port 53. Now, I didn't put UDP in front and I didn't put TCP in front because I want to capture the traffic whether it goes over one transport or the other. Click on OK. Now it's set up, port 53. I'll click Start. And now we're just waiting for some DNS traffic. So I'm going to toggle over for a moment, take a break, toggle over, do some web browsing, and then I'll come back and view the DNS traffic that I captured. Remember, if you see me go to a web page and when we look at the DNS queries, we don't see DNS queries for a page, it indicates that I've already been there and I have that information in cache in my local system, or I have it in a host file. From this location, I'll go to www.google.com. Now I'll go to ebay.com. Now I'll go to espn.com. Now you see how slow it is to get to ESPN? Now the nice thing here is that when we look in the trace file, we should be able to tell if the slowdown is because of the DNS response times. If it takes a long time to get to the DNS server to get to the ESPN web page, that could slow down the feel for web browsing. Let's toggle and see what we have in our trace file. Here are the queries that I have. There we can see a query for Google. And we see a response that came back. Now, in the time column value, when you're troubleshooting slowness in performance, you may want to make sure that your time display format is set to show you the seconds since the previous packet. That way you can see big gaps in time. So I can see the time between the query that went out for Google and the DNS response that came back. And here's the query that went out for ESPN, and here's the response that came back. So at this time, it looks like the typical response time is 0.01 seconds or 10 milliseconds response time from the DNS server that I'm talking to, which is 68.87.76.178. There we can see all of these different queries going out. And I didn't go to that many websites, but if you look at something like ESPN, you'll see that when you go to ESPN, they will feed you to their ad sites, various ad sites. So you make all sorts of queries to go out to these different web pages. Whereas you can see something like Google, when you go to Google, you go to Google. Here we can see a little bit further on, there's all ESPN information as well. Now I know that I went to the eBay site, but I don't see my query for eBay. Now it's kind of hard because I've got so many different queries in there, I want to make sure I'm not missing it. So in that case, I can go down into the trace, and I will just select the line that indicates that this is a query. That single bit there indicates this is a DNS query. I'm going to right mouse click and prepare a filter based on this value. There it is, dns.flags.response equals 0. I'll apply that. And now I'm just going to sort the info column. Now I can see it alphabetized there, and I don't see eBay showing up. And that, of course, has got to mean that I've got that information in cache or I've got that information in a host file. And on this system, I'm not using a host file, so I must still have it in cache from going out to eBay at some point earlier, within the time to live value that I received in the last DNS response when I went to eBay. I'll clear out this filter. And now I'll open up an existing trace file and pull all the DNS packets out of an existing trace file using a display filter. So I'm going to stop capturing, clear all this out, continue without saving. Now I'll open up a recent trace file. This trace file is called client dying. It's very easy if you want to pull all the DNS packets out of an existing trace file. All you simply have to do is, in the display filter area, just type in DNS. It's a recognized syntax name for a display filter. I click apply, and now we have all of the DNS queries and response packets that were seen in that trace file. I'm going to open up another trace file that has a number of DNS queries in it so that we can do some more interesting filters based on the values inside of those packets. I have a trace file called DNS-MISC2. And it has a number of DNS queries and responses, and it appears that a capture filter was used because all we have in this trace are DNS queries and responses. Now, as I showed you before, you can go inside of a DNS packet, right mouse click, and prepare a filter based on the selected value. The reason I use prepare a filter instead of apply as a filter is because I'm just trying to show you what the syntax is in the display filter line. You don't have to use prepare a filter first. If you're ready to apply the filter, just select apply a filter. I'll scroll down. Here, maybe I want to know how many packets have one question in them. I'll right mouse click and prepare the filter on this. And there is the syntax. DNS.count.queries is equal to 1. I can change that and say DNS queries are greater than 1. In that trace, nothing matched that filter. So I'll clear it out. In addition, if you look at the DNS communications, the response packets, you'll see a field in here that's not actually in the packet. This is the DNS time field. When you highlight any field in the packet, in the status line it will tell you the syntax name for that field. That will help you a lot in building filters based on field values. I can right mouse click on this field and say that I want to prepare a filter based on the selected value. It will put in the DNS time for that packet. DNS time is the time between a DNS query and a DNS response, and Wireshark will correlate the two using the transaction ID field. I don't care about any other DNS packet that had that exact same response time. I want to find ones that took longer than, let's say, longer than 10 milliseconds. And we can see a number of these took longer than 10 milliseconds. This one is 11 milliseconds. The first three numbers are milliseconds there. So we can see that quite a few of these response packets were greater than 10 milliseconds. I want to see if any of them are greater than, let's see, 0.04 seconds. And I'll hit enter. 3 of these responses took longer than 0.04 seconds. This one right here took a little over 1/10 of a second. And that's actually a long time in networking. Now I'll clear this filter out. And I want to show you where you can get the master list of all of the DNS filter syntax names. I'm out at the Wireshark web page, and I'll select Documentation. Scroll down, and here we can see the display filter reference. I'll click the link. I will scroll down to the display filter reference, click the letter D, and here we can see the list of all of the protocols and applications that Wireshark can decode. See down here you've got domain name service. I'll click on that. Scroll down. And here are all the field names that DNS uses, as well as some additional ones such as DNS.time. There isn't really a DNS.time field in a DNS communication, but we can build a filter on that. So here we can see the DNS count additional resource records, or the DNS count queries, which we did. Let's scroll down. DNS response, which is going to be either on or off. Yes, it's response. No, it's not a response. DNS ID, the length. Now if we scroll down, we can see there's DNS time. So this is your master reference area for creating the advanced DNS filters. Don't forget that if you make a really nice DNS filter, such as the DNS time filter, you right mouse click, prepare the filter based on the selected value. Oh, let's say it's greater than 1 second. If you really like that filter and you're going to use it again, you can click the filter button. And here we can see down at the bottom we have a new filter, and we'll say DNS time greater than 1 second. I'll click on new so that now that new filter will show up at the bottom of the list. Say OK. Luckily I have no DNS responses that took longer than 1 second from the DNS query time. But later in this section you will see some problems with DNS communications, and applying a filter like that will show us the packets where we've had a slowdown in communications. Now I want to finish this section off with one final filter, and this filter will look for all DNS responses that indicate there might be a problem. So I'm first going to open up a trace file, and this file is called DNS-server failure. Now I've got that filter still sitting in there from before, so obviously I don't have any DNS times greater than 1 or the packets would show up. I'll clear out that filter, and now I'm seeing a series of DNS queries with responses that carry some sort of error, such as no such name or a server failure. Now if everything goes well, in a DNS response, we should be able to look inside the DNS packet, and at the end of the flags field, we should see a reply code saying no error. So that field should be the last 4 bits of the flags area should be a 0, and that is equal to this 0 right here where my cursor is pointing right now. So we want to build a filter looking for reply codes that are not equal to 0. And that should be able to bring up our server failure packets and packets that have the reply code saying no such name. While I'm clicking on this field down here and selecting it, I'll right mouse click and say that I want to prepare a filter, but I don't want the selected value. I want to get packets that do not have the value 0 in that field. A server failure packet has the value 2 in that field, and a no such name response has the value 3 in that field. The syntax of my filter is exclamation point, which means not, and then dns.flags.r code, response code or reply code equal to 0. So we don't want any DNS reply codes that are equal to 0. Always remember to test your filters. So I'll click apply, and unfortunately there's something wrong with this filter. I see some DNS queries in this trace. And the reason I see those DNS queries is kind of interesting. If I highlight a DNS query packet that matched my filter, I'll look in the flags area, and here's the flags area. It's 2 bytes long. The last 4 bits is the response code area, right? Well, unfortunately, there are no response or reply codes in a DNS query. So the field doesn't even exist in this particular packet. So it sees it as a DNS flags area where the reply code would be, but we know that there is no reply code in a query packet. So what I want to do is I want to say that the packet has got to be a DNS response packet as well. I don't want the DNS request packets to come up there. So I've highlighted packet number 2, and here's the bit that indicates whether it's a request or a reply. The response packets contain a 1 in this area right here, this 1 in this first bit location, and queries will have a 0 in that location. So I want to make sure that my packets match this DNS flags reply code of 0, and they've got to match this single bit setting, meaning that it is a response packet. So I'll right mouse click, prepare a filter, and I'm going to AND together the value in this field that I'm highlighting with the existing filter. This is the syntax now. So it cannot have this value on this side, the DNS flags response code or reply code of 0, and it must have the DNS flags response value of 1, which means that it is a response packet. I'll apply this filter to test it and see if it works. And there you go, it works. So all of my packets appear to be response packets now. I'm not seeing those requests going out, the queries. And all of these have some sort of a fault in them. They don't have the value 0000 in the reply code field. They have some other value that indicates that things did not go well. That is a great filter, so I'm going to save it. We can see it's placed the filter string down below. I'm going to call it DNS response error. I'll click New, and here's my new filter down at the bottom of the list. And I'll say OK. We're going to start by looking at normal DNS communications. And I've opened a trace file called dns-ok.pcap. And in this trace file, we can see that the user has gone out to make a standard DNS query for www.iana.org. In the DNS portion, the middle window, I'll right mouse click and expand this subtree. We can see that this is a query packet, because if it has the bit set to 0 there, that means it's a query. If we scroll down, we can see there's one question in this packet, and scroll down a little further and we can see there's the query for www.iana.org. The type is A, which means it's a host address, and the class is IAN, which is Internet. We see a response come back. Wireshark will correlate the request with the response in the line directly underneath the domain name system heading, and it will also tell you how much time passed between the request and the reply. Here we can see the first bit is now set to on, which means that this is a response packet. As we scroll down, we can see that there's one question being restated in this packet, and there's one answer. Here's the question up above, www.iana.org. And as we go down into the answer section, scroll down, we can right mouse click and just expand the subtrees. We can see that the name www.iana.org resolves to 192.0.34.162. Now just a note on this line. I'm highlighting this line up above where it says www.iana.org, and down below you can see that I do not have www.iana.org highlighted. Instead, this is telling me that this is a repeated field. In other words, go somewhere in the packet and get the value. And the value is at offset 0C. That's 12 bytes into the packet, at least 12 bytes, I should say, into the DNS portion of the packet. And that's where iana.org, this line here, www.iana.org, sits inside the packet. So it's a little strange when you look at the responses and you see that even though it appears like www.iana.org should be seen multiple times in the packet, it's not. So this is a normal DNS communication. We have the query that went out, we have the reply that came back, we got an answer, and we got an IP address. I'm going to open up another trace file now. This one is called nst-nslookup-all. And this trace file is in the DMP format. Here I can see that I've got a DNS query that goes out looking for a host, novell.com. Now it's not looking for www.novell.com, it's looking for novell.com. This is NetScan Tools doing an NS lookup process. So here we can see the query has gone out for novell.com. The second packet that came back gave us an IP address. But look at this portion in the second packet. We have one question, one answer. We have 3 authority resource records and 3 additional resource records. Let's look a little further into this packet. We'll scroll down to the answers section. There's the query section up above, and here's the answers section. Now in the very first answer section, we can see simply that we have novell.com, type A, class internet, and the address assigned to novell.com. This entry is allowed to live for 6 hours in cache on the local system. So there's our basic response right there. But then we also have authoritative name server responses. We can see here is one, novell.com, and the type is NS, which means name server. We can see authoritative name server. So there's our name server, ns.novell.com, and you're allowed to keep this information for 23 hours, 57 minutes, and 12 seconds. As we scroll back down a little bit further, we got another answer from another authoritative name server. We have ns.utah.edu, and another one, ns1.westnet.net. And now we're into the additional records portion. Now in the additional records portion, you'll see that we have an answer saying ns.novell.com has the IP address of 137.65.1.1. So not only are we getting the authoritative name server list by doing an NS lookup, but we're also getting the IP address of each of the authoritative name servers. And to make this simpler to read, I'm going to take the additional records section, and I'm going to right mouse click, and I'm going to collapse all first of all. Then I'll open up DNS, go directly to the additional records, and this section I want to expand the subtrees in that section only. So there's ns.novell.com. I'll collapse that one, I've seen it. Here's ns.utah.edu, another authoritative name server. There's the IP address. And there's ns1.westnet.net, and there's its IP address. So in this query, one query for novell.com gave us the IP address of novell.com and 3 authoritative servers and the IP addresses of the 3 authoritative servers in the additional resource records reply area. The next DNS query that we see in this trace file is a specific record query, but it's not looking for a host address anymore. Now it's looking for a mail exchange entry for novell.com. If we look inside the packet, we can see it's just a standard query. We don't even have to open up the flags field. We can see that it's a query packet. We'll open up the query section, and we can see it's novell.com. The type is MX, and there it is, mail exchange. The response that comes back has one question, 3 answers, 3 authority resource records, and 6 additional resource records. So let's go and see what those answers came back as. I'm going to minimize the queries section there, collapse the queries section, and focus on the answers section. So in the answers section, we received three resource records for an MX value for novell.com. We got prv-mx.provo.novell.com, prv1-mx.provo.novell.com, and minotaur.novell.com. When we went into the authoritative name server area here, we have our three name servers listed. And in the bottom of that, we should have not only the IP addresses of our three name servers, but we should also have the IP addresses of our three servers related to the MX records. So there we can see PRV-MX, PRV1-MX, and Minotaur. And they're the IP addresses of each of those. The next query that went out from NetScan Tools when we ran this was a query for any at novell.com. And here's the response that we received back. Now I'm going to collapse this for a moment. Oops, sorry, I'm going to collapse the query portion. It's already collapsed, good. We'll go into the answers section. We can see right here we have one question, and we have four answers, and we have three resource records and three additional records. So let's go into the answers section first. Here are our answers. We have novell.com, the name server. So the first three responses we have are the name server. The last response there is the start of authority. That's the start of zone authority. And the entry we see there is mname, which means main name. And that's supposed to be the main name server for that zone. If we open up the authoritative name server section, you'll see there are name servers listed, and the additional records should give us the IP addresses of our three name servers and the IP address of the main name server if it is different, which, as you can see, it's the same as the one above it. It's ns.novell.com. That's why we only have three records there, because we've got ns.novell.com has two responsibilities. It's not only a name server, but it's also the primary name server for novell.com. Now the next packet that we see in that communication is a pointer query. And this is when we have an IP address and we want to associate the name with the IP address. So in the query section, if we look at just the query information, I'll right mouse click and expand that subtree. We can see that the query was for 1.1.65.137.in.addr.arpa, and that is the IP address, but it's listed backwards, starting from the top of the tree in naming convention for the internet. So we have, when we read it backwards, it's ARPA in-addr 137.65.1.1. That's the format that we have to place it in when we make a pointer query. And here is the response that came back to that pointer query. The query is being restated, and we can collapse that. And here's the answer that we get back. The domain name server. That's ns.novell.com. There are the authoritative name servers. We see NS2 and NS, and there are the IP addresses for each of the authoritative name servers. Now the next portion in this trace is kind of interesting, because instead of seeing DNS running over UDP, as we have all through this trace, we now have a handshake going out to port 53. This is DNS over TCP. And this is used for a zone transfer typically. So here we see our client going out to 137.65.1.1 ns.novell.com. We see a SYNAC come back, and we see the ACK finish up the three-way handshake. In packet number 12, we see a TCP communication go on a cabling system, and the data only contains 2 bytes. Now we're going to pull out that one conversation by right mouse clicking on it and following the stream to see what was said from the client to the server and from the server to the client. From the client to the server, novell.com is contained in the packet, and from the server to the client, novell.com is contained in the packet. So we'll close this out, because all we needed to do was filter on that one stream. All we see is a handshake at the beginning. Then we saw this little short packet go out, an acknowledgement for receipt of that packet, Here we are in the acknowledgement that came back. Then we see the DNS query going out. Now this is a zone transfer query where we see AXFR. That's a zone transfer query. So I'm going to close the TCP header down because we'll be focusing in on the DNS section of this packet. Scroll down. There we see the query section. And there it is. Just simply the type, instead of being a type A, it is a type MX, it's an AXFR, which is, of course, the zone transfer request. Now in this case, there was authorization required in order to do the zone request. So the server that we went to refused the zone request. And that information is in the flags area. We see the response. There we see it's a response. And here's the reply code. And up until this point, we haven't seen anything in the last 4 bits of this flags area. But that is where we would have a reply code. And the reply code came across as 5, which means refused. And the reason why we see novell.com again in the packet is because the question must be restated in the packet. We see the finishing of that connection. That connection is done at packet number 20. We'll clear out our filter and see what happened after packet number 20. We see a pointer query go out. And a little further in this trace, we also see a zone transfer attempt again. Now in packet number 21, this is a response packet, a pointer response packet. In the DNS packets, you'll see that Wireshark will correlate the requests and the responses. And if you want to quickly go to a request, when you're looking at a response, you can just double click on that field and it will take you right to the request packet. Same thing if you're in a request packet and you want to go to a reply packet. You would just double click on the field that explains that. So those are actually normal communications, except certainly it's not normal to see a zone transfer packet refused. Just as in the last section we were working on capture filters and display filters, we can build a display filter for all of the refused packets. What we have to do is go down to the reply code field where it says refused, right mouse click, prepare a filter based on the selected value, and we can see there it is. dns.flags.rcode response code is equal to 5. In the next section, we'll start looking at some DNS faults and slow DNS communications. I've opened up a trace file called dns-serverfailure.pcap. And this is an interesting trace file because we have a number of different types of DNS response codes showing up in there. You can see in the right-hand column we have a pointer query trying to resolve a name to 192.168.1.109, and the server comes back and says no such name. Well, that's the local network address. That's one of the systems on the local network. So the server's not doing a lookup on that one. I mean, it just doesn't have any name entries for the local systems. So here we can see a reply code of 0001, which is equal to decimal 3. We can build a filter based on the reply codes and say we're looking for any reply codes that are not 0000 in order to see all the different types of replies that can come back that might be in this trace file. If this reply were all zeros, then it means that it's okay. That's a normal query and a normal response would come back with that. For example, packet number 6 is a standard query response. I'll click on this one and we can see there's no error in there. But packet number 2 gave us a no name response. In packet number 4, here we have a server failure response. Now a server failure response would be a code 2, an R code or a reply code 2. And that may be something such as the user was making a query to the DNS server, and the DNS server had to ask on the user's behalf. So it did a recursive query to other servers, and then a timeout occurred. It didn't get a response in time, so it turned around to the user and said, I'm sorry, there was a failure. This lookup just didn't work. It doesn't mean that I don't have a name for you. It just means the DNS process did not resolve properly for you. So here we see a number of different queries in there. And as you scroll through this trace file, you might notice a strange one in packet number 5. We have a query, somebody doing a DNS query for 127.0.0.1. And it's one of the stranger responses you might see in the world of DNS. Number one, nobody should be making a query really for 127.0.0.1. That makes no sense at all. That's the loopback address. But let's see how the server responds to that. In packet number 6, we can see that the response comes back with no error, which sort of implies that the DNS server did resolve that and it has an answer for the client. Let's collapse the flags area. And this is what's strange. We see the question being restated in a response packet. We see that there are no resource records in the answer, but the client has been given 13 authority resource records and 13 additional resource records. And if you look a little further into the packet, you'll see what the authority responses are. They're the authoritative name servers, and what it's giving the client is the list of root DNS servers on the internet. I'll open one of these up so you can just see the inside of it. We can see that we have m.root-servers.net. We have L, K, J, I, H, and there are the 13 root DNS servers on the internet. Not only are we getting all of their names, but in the additional records area, we're getting all of their IP addresses, which is really an interesting query and a response combination to see on a network. You should never see that on a network, to see this 127.0.0.1. That's an application that the client is running that does all sorts of different types of name resolution. They're not supposed to be running it, but they were. Now let me open up another trace file, and in this case we're going to look at problems that are between a client and they're trying to web browse to a server, but nothing goes right from the beginning of the web browsing session. Select Open, and this trace is called Another Lousy Hotel Network. Now in this trace there's a lot of ARP traffic at the beginning of it, and I don't want to see that ARP traffic, so I'm going to apply a display filter. Exclamation point ARP, and I'll hit return. Now the first packet in that trace is simply a part of the update process for Windows, so we'll ignore that one. But here we can see the client system going out and doing a query to 4.2.2.1, and it's looking for www.packet-level.com. There is no response that comes back, and my time column setting is set to show me from the end of one packet to the end of the next packet. Anytime you're troubleshooting slowness on a network, make sure that you set your time column this way. So here we can see that from the time the first query went out to the time the next query went out, we had approximately a 1-second delay. Now the first query that went out, we can see the transaction ID is 0001. The second query, which is a duplicate, has the same transaction ID. It's not the exact same packet though. And the way you can tell is if you look at packet number 18, you go into the IP header, you'll see the ID field is at 000B or 11. If you go to the second query that went out, we can see that it's a different IP header. This one is 000C. We'll close up the IP header. We're looking at the second query that went out. Now we know that this is a client that didn't get an answer to the first query, so it's going out and it's making a second query. Now right here we know that we already have a 1-second delay just caused by that duplicate request that had to go out on the cabling system. In packet number 20 we have a response, and this response is tied to packet number 19. Here we can see it says it's transaction 1. There is a response, there's no error in there. And we'll scroll down to see that it gave us the answer. There's packetlevel.com. There's the IP address. Now what's interesting in this trace file is that there's a second DNS response that came back. Packet number 26 is another DNS reply that came back because 2 DNS queries went to the server and the server processed both of them and sent 2 replies back. By the time that second reply came back though, the client had already moved on to make a connection to the server. The client had already shut down the listening port that had sent the DNS query from. So when we see the second query come along, here we can see an ICMP response from the client saying, destination unreachable, port unreachable. I'm not even listening anymore for your responses because I've already moved on and stopped listening. At this point, I'm not concerned that I have an ICMP destination unreachable, port unreachable on the wire. I'm only concerned as to why I had to do multiple DNS queries to connect to my DNS server and get a successful response back. That doesn't look too good. I'm going to open up another trace file right now where we will take a look at a DNS time to live issue, which is really strange. The trace file is called DNS-TTL-issue. Now here we see a DNS query going out on the wire for www.netanalysis.org. We see an ICMP time to live message come back. It says time to live exceeded in transit. If we scroll to the right, look at the whole thing. It says time to live exceeded in transit. We can see that it's an ICMP type 11 code 0. And when this message comes back, it's required that the device sending the ICMP packet retransmit back to the originator of the communications the original IP address and the next 4 bytes of the original packet. So we know what triggered this. Here we can check down here. We can say, what triggered this response packet? Sure enough, it was our original DNS query. There we go. There's our source IP address and destination IP address seen in packet number 1. There's our source port and our destination port that we used in packet number 1. But this time to live is a strange thing to see, because if I look at the original packet up above, if I look at the original packet up above, I want to know what the time to live setting was in that packet. So I'll open up the IP header, scroll down to the time to live field, and it had 128 in the time to live field. Well, I'm looking at the time from the end of one packet to the end of the next packet, and looking at this value of 1.8 seconds. We would either have had to go through a ton of routers to get to 204.156.128.1 to have somebody along the path trigger that response, or something else is going on here. And in this case, something else is going on. Because look at who triggered the time to live message. It wasn't some router way out on the internet somewhere. It was a system that appears to be on the same network, most likely, as the client. The client is a 207.33.247 IP address, and the one that responded is a 207.33.247 address as well. So it's actually this device that is somehow blocking our client from getting this data out onto the network to this DNS server. It could mean that this box right here, the 207.33.247.65, is holding that original packet long enough so that the time to live timer value expires. And then it just isn't forwarding that packet on. It's holding it, and then when it expires, it sends a message back and says, I'm sorry. The time to live, it didn't make it there because the time to live value exceeded what it was allowed to be. So it's a very strange communication, and we can see why the DNS, why the web browsing session wasn't working. It had nothing to do with HTTP. We never even got to HTTP. We couldn't do the DNS process properly. In that case, we might want to look and see if we have another DNS server that we can try. That's exactly what our client does in this case. Our client goes to a backup DNS server. We can see a second query going out to 204.156.128.10. But look who stands in the way. This 207.33.247.65 device again sends a message that says, I'm really sorry. Time to live exceeded in transit. Our client even tries a third DNS server. But again, that one box comes back and says, I'm sorry. Time to live exceeded in transit. Possibly 2 reasons here. Number 1, we're not supposed to be talking to these DNS servers, maybe. Number 2, this guy right here is getting in the way of our communications. So that's where we would focus on trying to figure out why this web browsing session didn't work. The error seems to be in the world of DNS. Let's look at another problem with DNS. The trace file I'm going to open up now is called DNS fault. Now in this trace file we have the DNS client, the client going out to the DNS server. It's going out to 10.0.0.1, making a query saying that I'd like the host address of ftpcorp1.nai. Kind of a strange request. Here we get the response that comes back, and it says ICMP destination unreachable, port unreachable. When you receive a destination unreachable, port unreachable message, it means that whatever port you are sending your query to or your traffic to is not supported on that system. It's not an open port. It's not available. So in this packet, I'll close down the IP header. There's the ICMP response message that comes back. We can see the original packet that triggered this was that query going to this machine at port 53. In this case, 10.0.0.1 is saying, look, I'm not a DNS server. Go away. Now I want to show you a trace file that's really strange, and I've seen it several times. I've seen this happen several times, but I'll open it up for you. It has to do with the wrong port setting in the response packets from the server. I'm going to clear out the filter that I had in that last trace, and I'm going to open a trace called DNS-wrongport.pcap. As we look at this trace, we can see already that we've got these destination unreachable packets coming across the wire. In packet number 1, we see the client system doing a DNS query, and we get a DNS response coming back. And then suddenly the client turns around and says, I'm sorry, I'm not listening on that port. It's a really strange series of events that's happening here. Because then we see the client making a query, we see a response packet come back, and we see the client say, go away, I'm not listening. Then we see a query, response, and the client says, told you I'm not listening. And then the client just queries a couple of times, and the DNS server is not answering at all. So we would look at this at first and think, what's wrong with this client? This client's having problems because it's making a query, it's getting an answer, but it's not processing the answer. That's not exactly what's happening. If we look at, let's look at the ICMP packet and what it's telling us. This ICMP packet is going to the client, and in the ICMP packet, we can see there is the response. It says destination is unreachable, the port is unreachable. Now it would feel like the client is saying, look, I'm not listening on this port anymore, and this feels like it's the client's fault because obviously it's getting replies. But let's look at what triggered this response packet, this ICMP packet. We see that the packet that triggered it came from the DNS server. The destination was the client's address, came from the DNS domain port of 53 to the client's destination port 1030. Now this is always the problem with these kind of packets. Whatever port you went to, the client is saying, I'm sorry, that port's not reachable. So let's go back to the DNS query that sits above these ICMP packets, these response packets. Here's a DNS query from the client, but it's not coming from port 1035 or 1030. It's coming from port 1035. When the DNS server is responding, it's responding to the wrong port number. So the client has no choice but to turn around and say, I don't know what you're talking about. I'm not listening on port 1030. The client makes another query, again, using source port 1035. It thinks that the DNS server didn't respond at all. DNS server responds, but it responds to the wrong port number. And that triggers the client to turn around and say, look, I'm not listening on that port. It's a very strange sequence of packets. But just remember, if you come up against something like this, look at that ICMP packet more closely and see what destination port triggered that ICMP packet. If I just looked at the summary information, I wouldn't have been able to figure out what was going on, and I would have blamed the client in this case. But it's not. It's the DNS server talking to the wrong client port. Maybe a moment ago that client port was open, and for some reason the DNS server hooked that and kept that port. In this case, we actually waited and then restarted the client system so it could build some brand new DNS queries to the server, but we waited a fair amount of time to hope that the DNS server would get sort of unstuck. In one situation that seemed to work. The second situation we worked on, it didn't work. We actually had to restart the DNS server. And from that point on, everything went fine, at least for a while, until it came back up again. If you haven't done so, I would highly recommend that you baseline your DNS communications so you know what's normal when you go to your primary servers that you always work on, or you know what's normal when you go to some standard servers that are out on the internet, such as eBay or Google or something like that. And that way you'll be able to look back when something goes wrong and compare between the time when things went right and the time when things went horribly wrong.